Hi, everybody.
Hi, Dr. Wen.
Hi. How you doing?
Good, how are you?
Good. You still president of the college?
Yeah, I still am.
Awesome.
Thank you.
That's gonna probably look good for transfer or even job.
Yeah, luckily.
They're gonna revote again
Hello.
this year. Are you running this year? Hi.
Hi, Dr. K.
Hi, Ryan. How are you?
Doing okay.
Glad to see you back. So we'll wait a minute for everybody to get on. I'll pick up where we left off. I think we were working on the first one and not completing it because I ran out of time. So, and the lab portion of it is still going to be practiced with the number system. So it should be all right. I think we should be able to wrap it up today. And then next week, we're going to do a little bit more hands-on with the simulator. Hi, everyone. Thanks for joining tonight. I think this class have about 40 something people. Okay, so while you wait, if you don't have the lab downloaded, you can download that one. We're gonna finish that toward more than halfway through. We still have to complete. I still have to explain the first assignment. I know some of you have submitted that one, but we still have to do the lecture piece on it.
Oh, Professor?
Yes.
After the part where we add the two binaries, is the when we first convert the hexadecimal, is it supposed to be to binary, or?
Yeah, so the problem, the example that I had there is for you to change it to binary and then convert. If you want, you can do it that way. I'm going to show a different technique. But yes, you can convert it to binary and then decimal. A lot of people do that because it's easier.
Oh, it's because it says here, it says convert, the first
To
one
decimal.
says the decimal value. Is that not
Yeah.
supposed to say binary, or?
No, I'll show you how to do that.
Okay, then. Just making
Yes.
sure.
Yeah, no problem. Okay, so it is 6:01. We have to get started. We are going to finish the first assignment, which is the in-class assignment, and then we are going to finish the lab today. And that's going to wrap up a lot of the areas with the number of representations. I'm changing this up a little bit since last year when I taught this, I used a gate design thing, which I thought was helpful for the engineering students. But I think I'm just going to get you directly into using Lc3. And so we're going to touch on Lc3 next week, and we're going to talk about how we're going to use the simulator next week. Okay. So I'm going to pick up where I left off. As I mentioned last time, we were still trying to finish the first assignment. And let me get into screen share here. And I think we finish off or we ended the session with just the addition, and we're gonna pick up where the hexadecimal portion starts. So let me minimize everybody on Zoom here. So we wrapped up the end of page 3, where it actually we've completed the addition. Give me 1 second. And then, so now I think we're gonna pick up where with the hexadecimal. And when we do the hexadecimal, we are gonna do some conversion, and then we're gonna work on the 2 complement. So with the 2 complement, we're gonna start with the binary 2 complement, and then we're gonna move forward to the hexadecimal 2 complement. It's a little bit different than CIS-7 in this class. As far as that part, because in CIS-7, I don't cover the 2 complement for hexadecimal because it would just be repetitive for many of the students. So here we are on page 3. So the example, I'm sorry about this. The example that shows you here, there was a question earlier about how we converted this from hexadecimal to binary. And for most people, when they need to convert it from hexadecimal to binary and then decimal, then what they would do is they would start with breaking it down to the 4 bits, so that way they can have the representation in binary. And then they would take the binary and then convert it back to decimal. And that would be easy for most people because it doesn't require, calculator or additional multiplication. So it's up to you. You can do it that way. So what I'm going to do is I'm going to do the number 1, showing you this technique. And then we're going to do another one where we would multiply it by 16 to the power of n, where we would use the multiplication method. So for number 1 on the convert hexadecimal binary on page 3 for our assignment, we're given this in hexadecimal. Okay, so I'm going to copy that and I'm going to put it here. And then what I would do is I would start with the 4. So the presentation or the representation of 4 in binary would be 0, 0, 0, 1, 0, 0. Because if you're looking at the most right bit, that's 1, that will be off. 2 would be off, 4 would be on, and then 8 would be off. Because hexadecimal convert to binary, there are only 4 bits of binary that would represent 1 hexadecimal value. So let me do it this way. 4 is equal to that, so you can see. Okay. And then the next digit that we're going to move to the right here, that's going to be your B. And you can start from right to left. That's up to you. But it's easier to type when we go from left to right. So B, and we know that B in decimal would be 11. Okay. And so if we convert that to binary, right, that will be redundant. But at the same time, what you would do is if you wanted to show this in binary, so that will be 8 plus 1 plus 2. So that will be 1, 0, 1, 1. Okay. And I'm simply, using addition subtraction method to convert that after we find the 11 in the scale for decimal equivalent to hexadecimal. And so the next digit is going to be 1, and that should be easy. 1 is 1, right? 1 in hexadecimal is 1 in decimal. So we can say that 1 is 1, or in binary, that would be 0, 0, 0, 1. And then lastly, C. Okay. C would be our 12. So that would be 8 plus 4. So first bit here on, 4 is on, 2 is off, and 1 is off. Okay. So as you can see, let me move this up a little bit further so you can see. If we write this out in binary, you would start with the 4 here, and you would have 0, 1, 0, 0. I put a space there so it's easy for me to see. And then 1, 0, 1, 1, and then 0, 0, 0, 1, and then 1, 1, 0, 0. Now, if you go through and if you wanted to go further in the decimal, to make this into a decimal, we can add up all the ones starting from the right and then go left. Okay, so I'm going to check it with my calculator real quick. So if I have 4, I'm sorry, I'm in the wrong mode here. Hexadecimal. If I'm in 4, B, 1, C, that would be 4, B, 1, C. If you look at decimal, that's 19,228. Why is that? Because remember, we have to add up all of these ones, and you're going to start from the right. Remember the scale, right? We have 1, 2, 4, 8. So 4 and 8 is added there. So you have to do a 4 plus an 8. And then after that, that will be 16. And then it's going to skip 32. it's gonna go to 64, skip 64, 128 skips 128, and then 256, we have to add 256. And then the next to 256, that's 512. And then after 512, that's 1024, it skips that. And then so forth. So you're gonna add up all the value that's gonna be equal to 1. So at the end, you would have a result where it would be 19,000, what is it? 19,228, okay? So in this technique, what are the steps, right? You can convert it, hex, to binary. And then from there, we would, use addition method to add up decimal equivalent of the ones. Okay. So this is one way to do it, and that's why I put that example here. Now, when you go to Cal State or UC, when they ask you to do these things, right, we don't have calculator and things like that. So this technique tends to be the preferred technique, where you can think about the 4 bits that would represent the hexadecimal, and you can do it in your head real quick. And then after that, you would add up all the equivalent values of the decimal that have the ones. Remember the scale that we did last time? Then you would have your output. So this one, you're only using addition, okay? And it's simple. Any question with this?
You said you can also use the power rule?
Yes. I'm going to show that right now. So on the next one, I wanted to show you how to use the 16 to the power of n using multiplication method. And this one is a little bit longer, so that way it works really well with that method. But again, right, like you have to multiply it out and then add it up. So the step in this is you would take the hexadecimal, this one, I'll copy this, put it in here so you can see. And then you're gonna start from the least significant digit, which is the far right. And then you're gonna go left. And every time that you go left, you're gonna increment the exponent by 1. So the far right is we're gonna start with the 16 to the power of 0. So for the sake of this exercise, I'm gonna start with F. I will write it out in each line so it's easy for you to see, okay? This is easier illustrating on the whiteboard, but I just want it to look a little cleaner because I'm not very good at doing touch screen with my finger. So 15, we know that 15 is F, right? And so the F is really gonna be 15 times 16 to the power of 0. And this represent the decimal equivalent of F, right? Because it's at the first bit. I mean, the least significant location. So that's really, when you multiply it by the power of 0, that's really this 16 to the power of 0 is a 1. So it is technically 15 times 1, which is 15, right? And then D, right? And if you remember the scale, D is, so A is 10, 11 is B, 12 is C, and so 13 is D. And since we move 1 to the left, we have to multiply this 16 to the first power. Then that will give us 13 times 16. And this is why if you can't, you either if you don't have a calculator, you have to multiply that out. You can plug that into your calculator and get a value. So on the next one, what we're going to do is we are going to move to B. So we have to raise the 16 to the next exponent. So B is 11, and that's going to multiply it by 16 to the second power, because now we're moving 1 to the left. Okay. And so for 1, sorry, I'm just not very coordinated today. All right, so that's gonna make us 1 times 16 to the third, because now we move 1 to the left again. Okay, then next we have the last digit, which is 8. And that's gonna be 8 times 16 to the fourth. Now, what do we do with all of these? We have to add them together, right? So officially, when we write this out, this is going to be, 8 times 16 to the fourth. And then plus 1 times 16 to the third. Okay, oops. And then plus 13 times, wait, I skipped this one. 11 times 16 to the second. Okay, so you see it now when we move to the left. For each of the digit, we increment it by 1 power in the exponent. Okay, and then 13 times 16 to the first. Now, if you wanted to be detail oriented, I keep it there so you can see. And then lastly, it's this one. Or I should say 16 to the 0. Okay. So this is the multiplication method. And once you multiply it out, then you add them together and you would have the result for this in decimal. Okay, so this is why you would see that the first method is preferred, because it's a lot simpler in that you just add. But if you wanted to multiply it out, if you wanted to use a multiplication method, you can. So it's more of a preference. Okay, now as long as you have the proper answer, I'm fine with that. Okay, but I wanted to show you how this is done so you know how it's done. Any question? Okay, so for the multiplication method, before we move on to the next one, start with the least significant position, and you're going to move left. And every time you move left for each of the digit, you're going to increment the exponent by 1. And that is the method. And if you look at the notes, I think I included that in the notes for you for this class, for the binary and hex notes. So when you work with Lc3 in programming, you would see that there are times that you would have to refer to memory location to see the actual output. The low level assembly, it doesn't really tell you, thank you. it doesn't tell you specifically, right? Because it's not like C++ compiler where it's just you have it C out. In order for it to show the value as text as human can see, we have to really point to the location of that value and then make sure that it's converted using ASCII or something, so that way it would see. So we have to encode it, use encoding system to show. So that's the next level. So on the high level language, the compiler, it handles all of that for you already. Where in the low level, you really have to manually work with it. Okay, so this is why we're doing this right now, because I don't know who you had for discrete structure. Some of you had me, which this is review for you. And then some of you have other faculty, they might not cover this. So sometimes it's difficult for students to see it. So that's why I'm covering it in the first week. Okay, thank you for putting the final output for that in the chat. Okay, so let's work with the next part where we're going to use the division method. Okay, and I just went over this with my class CIS-11 last night, but when you use division method to convert for binary and hex, your remainder is important. Okay, meaning that what happens? So in hexadecimal, when you divide it by 16, just like we're going in reverse now, right? We're going from a decimal to hexadecimal. You would take that decimal and you keep dividing by 16 until you cannot divide it anymore. Okay, until you get to 0. Now, every time that you get an output, you would have a quotient. And if you have a remainder, that remainder is of importance, okay? Meaning that we cannot ignore the remainder. So the way that we see this in programming is when you're doing like mod 16, right? It gives you the output for the remainder. So this is what's happening in the background. So when you're using those converter that's online, right? The programmer, they have implemented the mod or modulus in for that process. So what we see is it's explaining here when you look at a decimal value like this one, for the division method, we would take it and we would divide it by 16, get a quotient, the remainder we have to make sure that we note it, and that remainder is going to be the hex value at the end, okay? Now, the other approach to this is take the decimal, convert it to binary, and from binary, you convert it to hexadecimal, okay? We saw how that's done already earlier. So here in this example, I take 61453, 61,453 in decimal, and I'm going to divide it by 16. So when you divide that, the first step, you would get this 3840 as a quotient, and the remainder is 13. And this remainder is important. So 13 is going to be equal to D in hexadecimal. Then you're going to take the quotient and then you're going to divide it again. Remember? Like how we would increment the exponent, now we're going in reverse. So we're going to have to keep dividing. So then we would take the 3840 divided by 16. We have 240 as a quotient. And then because it's an even number, it divides evenly, you would still have to note that 0 remainder. Okay, a lot of people make mistake where they just like, oh, there's no remainder. I don't have to write anything down. Yes, you have to note that it's a 0 remainder because that 0 is the same as 0 in hexadecimal. Then you're going to take the 240 quotient and then you divide it by 16, you get 15. Okay, and there's no remainder again, so you get a 0. Then you have 15 left. I'm not done. Here, if you still have a quotient, you have to go one more step, even though it's smaller than 16, right? So you would take 15 divided by 16, it's 0, but you have 15 as a remainder, and 15 is F in hexadecimal. So when you write out the result, you would go F00D. And the last one is going to be the most significant. And the first step is going to be the least significant. So you're going to go bottom up, left to right. Okay. Very similar to binary conversion using division method. And I think I have an example of that in your notes. Okay. So let's look at the assignment. And here is just earlier we did the multiplication for 16 to the power of n. And I added some additional step for you there. I have a typo here. Okay. So let's try number 3. Okay. And in this case, we're going to have to do long division. And I think it would be better for me to use the whiteboard. So I'm going to take you to the whiteboard for a second here. Okay. So we have, let me check, 168, right? So we have 168, and we're going to divide it by 16. Okay, so 16 to the 16 is 1. That gives me 0. Bring the 8 down, right? 8 divided by 16 is 0. Okay, so we, to 0. So in this one, when you take 168 divided by 16, you get a 10 with the remainder of 8, you see? So I put an R8. Okay. Now, next, what we're going to do is we're going to take the quotient, because it's not 0 yet. We're going to keep divided by 16. So 10 divided by 16, it's 0, right? With an R10. So since this is the last step, this is going to be of significant. And if you want to make sure, you can also check if we have the decimal 168, what does it look like? It is A8. And why is it A8? Well, this 10 right here is going to be equal to A, and 8 is 8. So since this is the last step, the blue one is in the last step, so it's going to write out as A8. Okay, so 168 is that. And as I mentioned in the first day, if you wanted to handwrite this, that's fine with me, right? Some student, they scan it. Some student, they just use their smartphone and take a picture of their work. I'm fine with that. If you wanted to type it out, you know, not like in the division format. If you can use math symbols and things like that to do this. You can use LaTeX. There's a lot of different tools online that you can use. I'm not particular in the format that you solve your problem. I wanted to show you how to do this, so ultimately you would be able to solve this yourself on the test quiz or for future classes. Yeah, 10 is A. I'm sorry, I put, let me erase this part. So 10 divided by 16, you get 0 with a remainder of 10. And that remainder is important. So let me erase this and rewrite my R. Sorry about the chicken scratch. Okay, so that shows you how you can do that part using the division method. So you start with dividing it by 16, write down the remainder because that's going to be your hex value. Take the quotient, divide it again until you get to the 0. That's when you stop. So when the quotient gets smaller than 16, that is the last step. Okay. Can we put, yeah, you can do that. Now, when you program in assembly, right? In Lc3, you can just put X. You don't need to put the 0 in front. But for Microsoft ASM, like x86, you have to put the 0x because, and Microsoft ASM use C compiler to interpret assembly. You know, so they had advanced it a little bit instead of using like an emulator or simulator to kind of see your program. But so it understands 0x as an address. Okay. So yeah, you can put X, whatever, or base 16, that's fine. As long as you know it's a hexadecimal, that's okay. Okay. All right, so let me stop share on my whiteboard. Do you have any question for me so far?
By the X, is she talking about like where the 16 goes?
No, it would look something like this. Wait 1 second. Let me switch back to my screen share. So so in the case where if you, I'm sorry, I'm looking at the wrong one. So let's say that we got the result right from the last exam, the last question. We have a, what is that, 8, right? Some people, the proper way to denote this is 16, but in assembly programming, that simply is X, A8, or 0, X, A8. And by looking at this, we know that it is a hex value and it refers to memory location. Okay. So in other assembly language, you would use 0x and then your hex value. So in Lc3, you would find that it would, you know, it starts at 3000 and then it's going to increment. It's the offset, it's going to add to that location. So as you build your program, you're going to see that it's going to start at a specific address, let's say at 3000 A8, and then it's going to, depending on the operation, it's going to put it in the subsequent location. And by the end, it's going to be at a different location as you store the output, you know, with the different register. So something like when you're adding a 1 with a 1 to get a 2, you start at 3000 and then you're going to move to the next one and the next one. So it will give you the output in the later location after the hex 3000. You will see. I will walk you through this next week. Okay. Yes, I'm fine with you putting it this way, but you know, if you put it this way, that's the official proper way. But for our class, that just refers to the hexadecimal at a memory location. Okay, so you can complete 4. Okay, practice with 4. I didn't give you a lot of, you know, exercise to do in each area, as I just want you to know how to do it. All right, let's read the note for the adding. So for the adding, when you're adding, it's very similar to decimal addition, but you need to remember that hexadecimal has 0 to 15 equivalents to decimal. So when you reach the F, right, it comes back, it cycles back again. Okay, so keep that in mind. So here in this example, it says that they're adding 6A2 with 49A. Okay, and if you type that Beethoven, I don't know if you're using Microsoft Word, there's a little button on the top near bold, underline, and the strike. It says X and then a little 2. You can find that button there. It's in the home menu or ribbon, I should say, and you can find that there. Yep, you see it now, right? Okay. All right, adding hexadecimal. So they're adding 6A2 hex with 49A. So the lowest digit position is the 2 here with the A, and 2 plus A, remember A is 10, and you add the 2 to it is 12. So the decimal is going to be 12, and 12, there's no carry, right? Because when it reached F, you're going to have to carry. So 12 is equal to C. Okay, so this is why it has a C here. And that will be the hexadecimal after the sum. Now, in the next position, that's going to be the A and the 9. So the A plus the 9, so we have a 10 plus a 9 is 19, right? And remember, 19 is greater than 16. So we do have a carryover because when you get something that's higher than 16, you simply take 19, you're gonna mod it with 16, which gives you a 3 remainder. So you have a
Professor,
carry. Yes.
would that be G?
No,
16?
there's no G, there's nothing after F.
Okay.
It only goes to F and then it cycles back to 0 again. Okay, so
Yeah.
it's like how you add a 10 with a 2, and we would say 12, right? So it's carry the 1 to the next column, just like how we did with the binary. You're gonna carry that over. So here what happens is you have a 3 that's left and you're gonna carry 1. So with the 1, they're gonna add that carry 1 to the 6 and the 4 in the first column, the 6 and the 4, okay? So you have to carry that. So let's practice this so you can see. Okay, so maybe I'm gonna copy this real quick and let me go to the whiteboard. We will have to make do with Zoom, you know? Okay, so let me add text. Okay, and I'm going to take out the 16 so it doesn't confuse you because it didn't. So we're adding these, and these are our hexadecimal. Okay, and I'm going to switch over to draw. Okay, so we're gonna, oh, see that? Let's see. All right. I was trying to use my touchpad. Okay, so a C, what's a C? A is 10, 11 is B, C is 12, right? So 12 plus 12, 12 plus 2 is 14. And 14 is a what? If C is 12, then what's D? 13, right? E is 14. Okay, so here we have an E to the right. Okay, B is 11 plus 3 is going to be what? 14, right? Another E. So B, Ugh. Never mind. So 11 plus 3 is going to be 14. What's F? F is 15, right? 15, that's already at the end, okay? So when you add 15, so if you take 15 plus 8, what's that? 23, right? Then you're going to take that 23 and you're going to mod 16. Okay? So when you mod 16, what do you have? You have 7, right? Because if I take 23 divided by 16, that's a quotient of 1. And if I take that, subtract, that gives me 7. Okay? So we have 7 here with the carry. So I take that 1 that's carry, 1 plus 1 plus 7 is 9. Okay. Do you have any question for me? Is that okay? Okay. So that was number 5 from the assignment. So when you have it higher than 16 in this technique, when we add it, remember we would take that sum and we mod it by 16, whatever's left, what the remainder is 7. So that remainder value goes here and we carry the 1 because there's only 16 number in the in the hexadecimal system, 0 through 9, and then A, B, C, D, E, F, stop, right? Okay, no question, right? Okay, so that was number 5. And then you can try number 6. So real quick, right? 4 plus 9 is 13. What is 13 equivalent to? A, B, C, D, E, F, or what? Which one, right? Put that letter down. 0 plus 9 is 9. 6 plus A is 16. 16 mod 16 is 0 with the 1 carry. I'll do this one with you because I think you might be confused. Okay, let's add it. Okay, so we need to add these. So 4 plus 9 is 13, right? A10, B11, 12, C, 13 is what? D, right? So D here. 0 plus 9 is 9. A plus 6 is 16. A is 10 plus 6 is 16. You would take 16, you're going to mod it. 16, which if you mod this, it divides evenly. So 0 remainder. So we put a 0 with the 1 carry. And D is 13. 13 plus 1 plus 5. That's going to be what? 14 plus 5 is 19. And then we mod it again. That's going to be 3. Okay. So that will be 3 with the 1 carry. Okay. Any question?
Nope, that was good.
All right, awesome. So that wraps up the assignment, I think. And then now I'm gonna do the lab. We're gonna talk about the lab, which is also a conversion exercise and such. Okay, the lab. All right, let's move back up. So I'm going to refer to the notes real quick because I put this here for you. Actually, no, we'll just use this, but the notes give you some information about 2's complement. So any sine number, or what we see as a negative number in our world, the computer see it as sine number. And sine number, the way the computer understands it is a 2's complement of the unsigned number. So when you say 13, positive 13, right, and you wanted to make it into a negative 13, when you type in negative 13, the computer stores the 2 complement of 13 in binary. Okay, so how does that happen? First, what you would do is you would take the value. Let's say that this is our starting value, 1, right? A positive 1, and we convert it to binary. So this is our binary value. Then we have to use the not operator, or we reverse it. And the way I say this is you flip the bits. The 0 becomes 1 and the 1 becomes 0. So when in assembly, at this point, if you wanted to make it the first complement, or complement 1, you would take the binary or that value and you would not it. You would apply the not operation. Okay. So when we not it, you notice the 0 becomes the 1 and the 1 becomes the 0. Okay. So after we flip the bits, this is what we have. Then we're not done. That's only complement 1. Then we would add the 1, just a 1, right, to it, which makes it 2's complement. So there are multiple steps, right? Get it to binary, and once you have it at binary, then you flip the bits or not it. Then after that, you would do a +1. Okay. And that's where you get the 2's complement. So the positive 1, when we're trying to say that if it's a negative 1, the negative 1 is represented like this. And I mentioned that last time that the computer is going to use, the processor is going to place all the 1s in the front to indicate that it's a negative value. Okay. So for somebody that's not familiar with this, they would think that it's a very large decimal. It's not. It's just a negative value when you see a bunch of 1s in the front like that. Okay. Okay. Let's do one here. For the first question in the lab, it tells you to do the 2's complement. I had a little bit of time earlier, so I typed it out. So it doesn't take me too long to type it out while you're here. So we're given this value, and the complement 1 of this is to flip the bits. Okay, we're gonna not what we're given. Okay, so what does that mean? That means that the 0 becomes the 1, the 1 becomes the 0. Okay, and the 0 becomes the 1, and the 1 becomes the 0. Okay, are we okay so far? Any question? Oh, I hate Zoom menu bar so much. Sorry. It's just not cooperating with me now. Chat just went away. Okay, sorry. If I don't see your chat right now, I'll check in a little bit. Then next part is we're gonna do a +1 to it. We're gonna add 1. So we're gonna take what we have after the not operator, and we're gonna do a +1. So when you line this up, the 1, the add 1 is here. So the output of this is gonna be 1. Okay, it's just gonna add the 1 to the 0. Now, if you have the 1 in the back right here, then you would have to do a carry and all of that good stuff. Okay, so what will happen is, remember 2, 4, 6, 8, this is a byte. In a word size, there's 16 bits. So what will happen is the computer is gonna put in all the ones in the front of that value to show that it is a Sine value. Okay. Now, if you're going from negative to positive, right, the 1s becomes the 0 when you flip it. So it eliminates all that 1s in the front to show that it is an unsigned value or a positive value. Okay, so remember the steps. You will be asked to do 2 complement for quiz and exam. So start with the value, flip the bits, plus the 1, and you would have the output. Okay, next one, you can try that one. So this one's easy. Knot it and then add 1. So when you knot it, it's going to become 1 0 1 0 1 0 1 0 plus the 1. That just add the 1 to the end, and that takes care of it. Okay. So why do we care about this? Okay. When you operate subtraction in assembly, you add the 2's complement of the value. Okay. So if I'm saying, if I wanted to add, if I wanted to take 12, subtract 6 in assembly, we put the 12 into the register and we put the 6 into another register and we knot it and we add 1 to it to make it a complement, the 2's complement, and then we sum it. Okay. You see? Because you don't have the compiler to handle some of that back end. You just gonna have to think about the steps on how you would subtract. All right, no question on 2's complement in binary.
You said, so when we flip it, it's already the negative number, or do we have to
No,
add that
not
1?
yet. You have to add the 1 to make it a 2 complement. When you flip it, that's what we call the 1's complement. Okay. So the 1's complement is when you apply the not operator. Not done. Okay. It's not negative until you do a +1. Okay.
Oh, okay. Does that +1, like, what does it really do in the code? Is it just like, does it tell it that it's negative, or?
No, so you introduce the signal to what is here, right? And what that would do is it fills up that bit, and then also it's a process of just adding that particular bit to the output from the not operator. This is the way that they came up with to schematically make sure that it is a negative value. It does. So in the code, what happens in assembly is this. So like my example from earlier, right? If you're taking a 12 and you minus a 6, you know that this is a 6, right? In you know, if you do C++, you said variable 1 is 12, right? Variable 2 is -6, right? And then you add them together, or you can subtract a certain variable using arithmetic. But in assembly, this is what's going to happen. You're going to need to put one value into a register. The other value, doesn't understand a negative value until you operate the 2's complement. The second one, think of R2 is another variable, right? And then what's going to happen is you're going to have a third variable that's going to store R1 plus 2's complement of R2. So how do we do that? We would say R3 is equal to R1, I'm sorry, the sine R2 is equal to the 2's complement. So you have to take R2, right? You're going to knot it. And then it stores it to R2 again. You can do that, restore it back into the register. And then what you're going to do next is you are going to take the R2 is equal to R2 plus 1. That's how you do it in assembly. And then you're not done. Then you're going to have R3. Oops. R3 is equal to R1 plus R2. Why is that? Because at this point, I deleted the other one. At this point, it's already negative right here. Okay. So what that will do is when the processor understands that at this point, when you add the 1, it's going to take the value that you originally have, right, and store it in binary as a negative 6. So basically you're doing a 12 plus a negative 6. That's what you're doing. So this is exactly what you guys are going to be doing in the next few weeks. So okay, so you see how the code is? Any question?
And it makes sense with the number 0, how if you knot it, you get a bunch of 1s, and then you add 1 and it overflows back to 0.
Yes.
Which makes sense since there is no negative 0.
Yes, it overflows. It adds, it introduces that signal. That's correct. You got it. So now you see it. It will gel together. Trust me. All right, next. So that's just an example, okay? All right, do number 2. Let's talk about the next one. Now we're gonna do 2's complement of hexadecimal, and here's an example. So we have a hex, 6A3D, okay? And instead of converting it, so most people, this is what they do, and that's probably is an easier way, is, you know, they're taught to take the hex, remember we talked about the 4 bits, convert it to binary, knot it, and then plus the 1. That's fine too. I'm okay with that, but you have an extra step to do that. I wanted to show you how to do this because I don't cover this in CIS-7, only in 11, so that way you see the 2's complement of hex. It tells you here to create the 2 complement of hex, you reverse the bits and add the 1. The easy way to do this is to subtract the digit from 15. And then after that, you would add the 1. So in this example, they take 6, let's say, just say 15 minus 6, you get a 9. Okay, that's going to be when you, it's like knotting it now at this point, right? And then you would take A, or 10, subtract 15, that gives you a 5 in difference. And then 3, which is the next one, subtract 15, you get a 12 in difference. And then D, which is 13, subtract 15, you get 2 in difference. So at the complement 1, this is the hex. But you're not done. You got to go to do a plus 1 to make it the 2's complement. So you would add the 1 to it. And when you add the 1, it's only going to impact this last one here. And in this case, so it simply is 95C3.
And that's negative number, right?
No, it is a 2 complement of this value, which is a different hexadecimal value. Okay, don't think about negative in this class because it's going to confuse you. The only reason why we say negative and positive, it only apply to decimal number. Okay, the binary and the hexadecimal system, the sign value is treated as 2's complement. When you say negative number, it's only for the base 10 system. Okay, the what we see that would be negative, that would be sign, is treated as 2's complement. So it is a different hex value, is a 2 complement of this. Okay. Yeah. So let's work on this one. I wrote it out, this one, for you so you can see. And this is the scale, so you don't have to look it up or remember. So, okay, at the complement one, the first complement, we would start. So I started with the 1 here, right? I take 15, subtract 1. Sorry, that's wrong. 14, which is E. So that's this one right here. Okay. And then the one next to it. So again, I would do the same thing for the next one. 15, subtract 1, I also get an E. Then I go to the last one here on the right. I take 15, subtract 8, should give me a 7. Okay. And then, sorry, just giving you whiplash right now. Okay. Then we would take the last one, which is E, 15 minus E, or 14, which is 1. So the 1's complement of this is here. We're not done, right? We got to do a plus 1 to it. So the next step for the 2's complement is going to be, you would take this and you would do a plus 1. So what does that give us? EE72. Okay, so this is the 2's complement of the given, the required, the problem value. Any question?
Professor, we're mandatory required to put the 16, like the bases.
No, you can just leave it like that. That's fine. But I want you to get used to looking at it that way. So on the test or the quiz, you will see, I would say like decimal number, hexadecimal number, or sometime I would use the base. Okay.
And just to clarify, the hexadecimals are 16, the binaries are 2s, and then the decimals
Decimal
are
is 10s, and then octal is 8.
Oh, we're doing those ones as well?
I think I eliminated that. I don't remember, but let me check. Yeah, I don't think so. But
Oh,
okay. Okay. So for number 5, it says convert the Sine decimal integer to hexadecimal. Do the following. First step is to convert the absolute value of the decimal integer into hexadecimal. Second step is to use the decimal. If the decimal is negative, create the 2's complement of the hexadecimal number from the previous step. Okay. So what you would start with is we are given a Sine value, a negative decimal value, 611 negative. It tells you to create the 2 complements. So first you got to treat it as an absolute value. Now we can convert this to binary and then from binary to hex, or we can do the division method, right? And with the division method, we would get a hex value and then be able to go from there. So I'm gonna switch over to the whiteboard real quick and work with you on this one so you can see how it's done. So we're given this in decimal. And I'm going to do the division method so that way, you know, we just talked about that, kind of keep you remember in your mind. So we would have, we would start with 611. You're going to treat it as an absolute value because we're going to do a 2 complement for it. Okay. Or what you can do is you can find a 2 complement of 611 and then convert it to hexadecimal. So I'm just going to convert it to hexadecimal and then find the 2's complement so you can see 16. So when I divide 611 by 16, I should have a 38 in quotient with the remainder of 3. And then after that, I would take the 38 and I divided it again. And so we can have what, 2 times that will be 32. So that will give me a 6 remainder. So that's an R6. And then I would take the 2 and I divide it by 16 again. I get a 0 with an R2. Okay. So this is not the first complement yet. We simply take 611 and we convert it to hexadecimal, right? So if you wanted to check, the easiest way to do this on a calculator, you can use the negative sign, of course, but if you do 611 in decimal, right, you should get 263. Okay, so 263 is 611. And this is hexadecimal. Okay, then what do we do next? We have to find the 2's complement of it, just like what we just talked about. So how do we convert the 2's complement of it? We would then take each of the digit and we subtract it by 15 and then we do a +1. Okay. So earlier, if you recall, right, we talked about that just now, that when we do the 2's complement, we're going to take each of the digit and we're gonna subtract it. So let's try that. Sorry, it covers my whiteboard right now. Okay, so we're gonna start with the 2 and then the 6. So 15 minus 2, which gives you 13. And then 15 minus 6, which gives you what, 9. and then 15 minus 3, which gives you 12. So from the left, right, your 13 is D, 9, and 12 is what? C, right? So D9C. And this is the ones complement. Then after that, we're going to do a +1 to get the second, the twos complement. So as 13 or 12 is C, we simply end up with D9D for the twos complement. So we started with this right here, right, to convert 611 to hexadecimal, and we end up with this. Then we take the complement of the decimal by doing a hexadecimal by subtracting each of the digit by 15. And then last step, to make it twos complement, we're going to do a +1. So the first complement is to do the 15 subtraction. The twos complement is to do a +1. Any question? So I'm gonna, I see a question. Okay, no, you just put, okay, so let me change to our assignments. Okay, so when you guys become a developer later, right, think about doing a video conference for educator that has a whiteboard adjacent to, like, able to share multiple screen. That can be implemented actually, because you just have to allow like the hardware to be able to see both area. We just have to keep flipping back and forth. Okay, so let's go back to the lab. So I'll type this out so you can see. What was that, R3? Yeah. And then 38 divided by 16. That makes it a 2 with a 32. Let me check my math real quick so that way I want to make sure I'm correct here. 32, which is an R6. And then 2 divided by 16, which is a 0. With an R2. So at the first complement, I have 263. And then the second, oh, I'm sorry. $611 is 263. The first complement is, what was it? 9. Minus 6 is equal to 9. And 15 minus 3 is equal to 12, which is D9C. And then the twos complement is D9C plus 1, which is D9D. Any question? Well, you said no earlier, so for 6, this is a larger number, so you would start with its absolute value, convert it to hex, find the first complement 1, and then do a +1, then you have the 2's complement. Okay, I like for you to show your work for these, because I know you can punch that into a calculator and find the answer, but I want you to know how to do it. Okay, let's talk about the next step. Convert the Sine hexadecimal integer into decimal first. If the hexadecimal integer is a negative, create its 2's complement, otherwise retain the integer as it is. Using the integer in the previous step, convert it to the decimal. For step 2, if the original value was negative, attach the minus sign to the beginning of the decimal integer. So when you get the output, you got to put a negative value there. So when we started with the negative here, we simply is doing a 2 complement of a negative, right? So like you're saying that it's a negative of a negative, which is a positive, okay? So you would start with converting this to converting it using the 2's complement. Okay, so we would have to look at it this way, and how do we go back finding the 2's complement? We would then take each of the digit, subtract it by 15, and then do a +1 with it. Once you have that, then we would change it to a decimal value. So 52A is equal to, right, 15 minus 5, which is 10, or A. And then you would do 15 minus 2, which is 13, or D. And then A is 10, so 15 minus 10 is 5. So at the first complement, or complement 1, you have it equal, so complement 1 is equal to, what is it, A, D, and 5. And then for the 2's complement, we simply just do a +1. So that will be 6. Type it out, so 86. And then we wanted to convert it to decimal. Then you would start with the 6, and then multiply it by the 16 power to whatever, right? So 0, 1, 2. So I actually have it like this. So A, or 10 times 16 to the 2nd power, plus D, which is 13. So 13 times 16 to the 1st. I forgot to do this. And then plus the last one is 6. So 6 times 16 to the 0. And once you multiply everything out, add everything up, you would have a decimal. Since we have a negative to start with, right? We created the 2's complement, we retain. So if the original value is negative, attach the minus sign with it. So after you have done that, put the minus sign with it. You can use your calculator to check to make sure if you're on the right track. Any question?
Wait, Professor, do you mind repeating what you just said, like that quick little short part?
Yeah, so once you have the decimal right here, remember what it says right here. If the original value was negative, right, we have a negative here, attach the minus sign to the beginning of the decimal. So once you have the sum added up here, then you just put the negative sign in front of that decimal.
Oh, because it's like a negative number now, right?
Yes.
Oh,
yes.
okay, I see what you're
Yeah.
saying.
Mhm. Yeah, so in hexadecimal and binary, there's no such thing as negative, right? We just have to choose complement of it. So start thinking it like that. And then what if you convert everything back to decimal, then we have to treat it as negative positive. Okay, so make sure that we put negative sign to result.
Professor,
Yes.
so when we're subtracting the 15, that's like us nodding it, like doing the
Yes,
opposite.
in hexadecimal, that's what this is like. When you see the complement 1, that's usually the not. Yeah, in binary we not it. In hexadecimal we subtract 15. Yep, and then
Okay,
we
thank
add
you.
the. You're welcome. So now you know a little bit more than yesterday, right? Some of you did this before. Okay. So you can try number 8, just like what we did in the previous one, right?
Professor,
Sure.
should the final answer for number 7 be positive or negative?
Yeah, so yes, it should be negative because let me show you. 52A with hex 52A. And then when we bring it to negative, you see how the output is negative. So if you start with the negative hex, if it gives you like this, then you need to attach the negative sign to the decimal after you convert it.
Okay.
Yep. Same thing with number 8, okay? That's why I put it here. Okay. So
Yeah, Eric, that's what I got.
okay. Any question? Okay, so let's talk about operators. Let's talk about operators. I think one of you is not on mute. Okay, I think Andrew got it now. Thank you, Andrew. Okay, so let's talk about the not and or, the logical operator. In a lot of textbook, the symbol that they use is like this, okay? When you're doing a not, it's like a little negative sign with the drop line. And then that will be not. I normally, for the test and stuff, I just put not and in text, like word. So when you have the and operator, you would see the upside down V or the hat. And then when you have the or operator, you would have the V. And then when you see it like this, that would be not X or Y. And then when you apply the parentheses like that, right? And with the and, it's actually not X and Y. And so you can start looking at the symbol or how that's used, okay? Now, this is a truth table, okay? So when you have, remember in in programming like C++ or other classes, they go over like true false for the truth table. Give me 1 second. I didn't do a good job of giving you a good truth table there. So let me pull this up and then I will upload it. Let me see if I put it in notes for you. I don't think I did. Okay. Yeah, let me copy the one that I use for CIS-11, which is a better one, and then I'll supplement that. Okay, 1 second. That's just the last part, so we're almost done. Hang tight. Oh, you guys can use the information. So if you're in my CIS-7, you will see some of this in the next week. Okay. But just to give you a brief thing going into this, and we can touch on it next week again if you like. But so with the logical operator, I know that many times you probably use this in higher languages, like you would say, if this and this, right? Or if this or this, you apply it for control statement. But what's really happening in the background is that inside the processor, you would have these transistors, and transistors are used for digital switch, where it would either connect the signal or break the signal. Something like this as an illustration. And so in the logic gates, right, in this case, when you're looking at the AND, what happens is both of the switches are pushed. Okay. So if you're looking at an if statement, like if you say if A is equal to 25 and 28, let's say. So at that point, when it sees the AND in your logical operator, it's going to push for both of those. Okay. So physically, that's what's happening with the switches inside the processor. So when that's applied, what changes is that when it pushed like that, the voltage is given to the input. So it's pushing these voltage and it caused it to close. So now in the case where we would use the other operator, right, you would have the other way where it's not going to push on both sides. It's going to open it up. Okay. And that's how the processor really physically determine how to apply these operators when you program it at a higher level. And in assembly, we have to make sure that it understands, right? When we NOT it, how is it going to be treated? When we apply the and the or, how that's going to be. So I will upload this later on so you can see, and sometimes you would see that it's drawn like this. So last year when I taught this class, when it was still on campus at the beginning, I had student design the gates for different operators so you can understand it. So when you get into like electrical engineering or computer engineering, you would have like digital classes where they touch on this, and you would be able to see how that's drawn out, or you have to do that. Okay. So when we're, for the sake of our exercises, see how we would see the or, it opens, and for the and it closes. For the purpose of exercises, all we care is those tables. Okay, so let's look at the and. So when you have A and B, you would have 0 and when you have 0 and 0, you get a 0. When you have 0 and 1, you get a 0. If you have 1 and a 0, you get a 0. 1 and a 1, you get a 1. Okay. So in the AND operator, when you have, anytime you have a 0, right, you would get a 0 output. Think about it, right? When you're doing an if, this and this, both of those areas need to be true in order for that if to kick in, right? When you're using an and, both side of the conditions needs to be true in order for it to go. If any time that it's 0, anytime that it's false, it's going to be false. Okay, so anytime that you have a 0 in the and, you get a 0 as the output. 1 and a 1 is 1. Okay, for the or, anytime you have a 1, okay, it's a 1. So a 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. And 1 or 1 is 1. So in the case where you're writing in Python or C++, you say if this or this, right? And it only care about it. The if would take place, it would execute the body of the if one of the criteria is met. Okay, it doesn't care. So if the first one is met, it's gonna go. The second one is met, it's gonna go if you're using or. So anytime that you have true with the or, it's gonna give you true. Okay, got that? And then the not is just the opposite. You already saw that when we did the ones complement. Okay, so going back to our assignment now with that in mind, or our lab. So when you do this, okay, so when it's saying, it's showing you how to not it. So find the not expression of A. That's easy. That's like flipping the bits at what we did earlier. The first one here become a 0. The next one is 1. The 0 becomes the 1. The 1 becomes the 0. 1, 0, 0, 1, 0. That's easy. So when you not this, you get this as the output. Okay, simple. We learned that earlier. For the next one, oh, I did put the table here. I didn't look far enough. Okay, starting with the right.
Hey, Professor, in the one just now that you just did, when you nodded it,
And you just change 0 to 1 and 1 to 0, just like what we did earlier.
oh, but we don't have to do the 2's complement?
No, when you
okay.
do a not expression, it's just a not expression.
Oh, but with the 2's complement, you have to do the not expression and then add one, right?
That's correct. That
Oh,
is
okay,
correct.
I see what you're saying now.
So this is what we call at that, when you're doing the 2 complement at this stage, it's the 1's complement. It's the step before. Okay, we call that the 1 complement. Okay, so for the truth table, you have this. Okay, so the output of this would be, the anytime that, so the 1 and the 0 is what because when we have the and in the mix, anytime you have a 0, you get a 0. A 0 and a 0 is 0. A 1 and a 0 is 0. A 1 and a 1 is 1. This is different than add now, okay? This is logical operator. It's not addition, okay? A 1 and a 1 is 1. A 0 and 1 is 0 because it has a 0. 1 and 0 is 0, and 1 and 0 is 0. Okay, so this is the output of this one and this one. Any question? So now you can solve for D. That's easy, right? When you use the and, anytime you have a 0, it gives you the result as 0. And the only one that gives you a 1 is the 1. 1 and 1. True and true is true. True and false is false. So for quiz and test, make sure we know how to apply operators, logical operators. Any question with this? I see. Okay. So next we are gonna, let me close that. Next we're gonna talk about, let me see, is there anything else? That's it, right? Oh, I think we have the OR. Here's the OR. We touch on the OR, so I'll do one with you. Oops. Okay, so anytime that you have a 1 in the OR, you get a 1, right? 0 or 1 is 1. 0 or 1 is 1, 1 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 or 1 is 1, 0 or 0 is 0, 1 or 1 is 1. When you start playing with this, you're going to see some pattern happening, right? Like later on, we're going to talk about when you have exclusive or when you have this, you know, when you not or, it's going to be equal to something else. Okay. So when you notice, if you do this one, you would see that when we have this and we OR this, we get this, we get it, the same thing, same value. Okay. And then you can solve for the next one. So in the OR, using the OR operator, anytime that you have a 1, it's a 1. When you use the AND operator, anytime you have a 0, it's a 0. Question? And then I'll add the gates information, I think, for maybe for next week when we talk a little bit more about gates. Okay. No question on this. If you're done, you can submit it. But before we go, I have some time, so I wanted to touch base with you about the installation of Lc3. And you can do this next week or this weekend or whenever. So going into, if you're looking at your module, I think I put some Lc3 resources for you. For the Lc3 resources, you can find this in the first module. Now, if you're using Windows environment, it works really well with Windows environment. There is if you visit the website, there is a Unix version of it. But if you don't have Linux or Windows, I recommend that you use the online resources that is included with, I should have put this here. Yeah, so in the first module, I will relink it for you. It is located in the course resources, I believe. Okay. You will find the online simulator. Is it here? Sorry. I would redesign these pages for you. I've taught this class quite a while now, so sometimes I forget where I placed it. Check. Yeah, so if you're using a Mac, that's what I'm trying to get at. If you're using an Apple system or a Mac OS, you have to use an online simulator. And you can find them, right? In the case where if you don't look at the actual course room, you can just simply search for LC3 online simulator, and you would find some GitHub, like this one would work. Okay. Now this is where you would write your code and it would look like this. Okay. If you've never seen LC3 before, and even when you're looking at ARM, it's going to look similar to this. The Microsoft ones, it has more instructions in, so what do I mean? Things like loop, add. So you notice that there's only add, branch. Branch would be applied like when you're using a loop or like control statement. So you would write it like how you, the sequence of it would be very the same as your other program, of course, but you have to handle it with operator, the logical operator, and register. Okay, that's like your variable. Okay, so when you
That code
visit,
you have? Oh, my bad.
yes,
I was gonna ask if that code does like the number stuff that we've been going over.
yes, and you're gonna start with the very basic, like 2 plus 2, and then you're gonna go to 4 multiplied by 2, and then divide, and then so I would teach you how to use the very basic to writing a recursive program, with stack and everything in LC3. So by the end, you would be like the LC3 Pro.
Wait,
So
it takes that many lines to do like a simple code like that?
yep.
Really? What
This
the-
one has loops. Yeah, it
Oh, I
branches. So you would have, so this one actually have loops. So in the case where if you wanted to do like a for loop, you would have to branch. And yes, it does take like 5 lines just to do one loop. So this, once you get it, it's like super easy. It's like moving numbers around, and yeah.
I was about to
But-
say, because in C++, you can do that in like one line, right?
So I'll tell you this though, not many programmer can program in assembly. Okay. And I can say that many faculty can teach programming, but not all faculty can teach assembly programming. And many programmers learn assembly in school like you, but they prefer not to do it because it's tedious. But it takes skill to really do this. Just like how you have people who program great in C++, but when they try Java, it's a little challenging for them because it's a little different. So once you get it, and hopefully by week 12, you're going to be like, oh, piece of cake. I can write the program for Dr. Wynn. That's no problem for my project. Okay. So have faith in the process. All right. So what we will do is we will talk about installation. So when you visit the website for the LC3, you can download it, and I'll show you how to do that. Now, once you download it and install it, it's going to dump it into the C drive. I get a little bug here. So this is the website from the link from the Lc3 Resources. And so when you click on this, right, it's going to take you to download, and this is the executable. When you run the executable, this is Windows now. You can have it located in a different directory, but if you just click unzip, okay, it comes down as a zip file, and then you click unzip, and then once it's unzipped, then you can, and basically that would be the installation process. So where does it go? Okay, after you install it in your Windows system, it puts a LC3 folder here. And this is where your simulator lives. Okay. You can copy and paste it onto your desktop if you like, or you can create a shortcut to this. When you write your program, you use an editor, just like how we would write it in text editor for our C++, Java program, etc. And then when after you finish writing your program, you save it as a .asm. All assembly program is saved as .asm. Now, sometimes that they would package it a specific way depending on the type of assembly language. I've taught this class in Microsoft ASM when I first started teaching at Moreno Valley College. The students, they completely hated it. They hated it, and one of them is working at the iMake Innovation Center, and he can tell you, he would say that it's horrible because you have to utilize a specific library with the C compiler, and there are a lot of things that could go wrong. So this is the easiest way that you can have good, adequate output. Okay, so you write it in editor. And then when you're done, you save it as an assembly file. And then you would use the simulator, and it looks like this. So earlier we talked about, and unfortunately I can't expand this. So when you run your program, right, we would start at the address 3000, and you see all the registers. Okay, so these are going to be the storage location, and you can load it. So when you load the data to it, right, remember that these are hexadecimal number. A lot of students are like, why is it a different value than number 12, right? 12 is in hex. Is it in hex, or are you trying to say 12 in decimal? So that's why I emphasized the first week about number system, differences in number system, and how you should see it. So when you look at this, you're going to see, and sometime when you move it across the register to do calculation or for a certain process, it's not going to be here. It's going to be somewhere in your memory and sometime further down the line here. Okay. So we will play with this next week, and I will walk you through the process on how to utilize it. You have a step through, run the program, the step over, you can pause it, you can set a certain value to a location so you can test it. So if you did a program that multiply, all whatever, right, variable that you have to a number 2, like you multiply everything by 2, or you do an exponent program, this is how you can test it, is through the test value button. Okay. And so you can see if it's giving you the right output. And yes, you have to use your calculator to convert it back so you can understand what it is in decimal, because it's going to give you in hexadecimal. And this is why we emphasize this. And you can go to a certain location here. Okay. So that kind of show you what we're going to be using. And that will be for next week. Okay. Any question? Okay, work on
so
the,
you
yes.
said, you said those numbers on the far left, those are your hexadecimal numbers, right?
So this is basically, hexadecimal number, right? But when you build your program, you don't start it at the top. You would start it earlier. Remember the website that we looked at? This one. See how they start? Lc3, you always originate at 3000. All assembly program, you would have an origination address. And so that way it knows where it's going to begin. Okay. And this is, this is just default. It's the common practice for Lc3. Yes, you can start it in the later, but the way the simulator understands it is you would start it at 3000. So it's actually further down. Okay. Yes,
Oh,
you're
it's
right.
like that IO stream?
No, IO stream is you using a library for input output. This is actually, we're locating it. So you basically point out a location in the memory where the program, what part of the memory where it's going to use to begin your program when it runs. Okay. It's going to load it at those locations.
So I suppose in assembly you can build higher level constructs, like say a function, but it's very tedious or something.
Yes. And one of my former students turned in a calculator program. It was like 1,000 something lines. So, and that's like more on the very basic calculator, multiply, divide, subtract, stuff like that. I opened that option up, but he ended up doing it. He got it working correctly all the way through. I tested it. It doesn't have GUI or anything. Assembly level, you're lucky if you would see text. It's not designed to be user interface. It's designed, you programming the processor at this point. So yeah, if you, when you display text, you have to convert it. But yes, you can write functions. You can write any program that you normally would write in C or C++, but we will see the parallel when we do this, right? But when you do that, yes, you would have a lot more lines in your code.
Like if you want to write a C++ compiler for a brand new type of processor, then it would have to be an assembly.
Mm-hmm. Yes. And before, you know, when they manufacture these processors, like we talked about RISC and CIS, right? Like you see how many ARM chip that's coming out for different things, right? Somebody's doing this, okay? If you look up job for ARM developers, there are lots, okay, for different companies in all different aspects. You know, not necessarily just for Apple. There are many companies that produce ARM processor. So knowing how to do this in Lc3 is going to give you the basic understanding. It's kind of like learning C++, but when you look at a Java program, you kind of have an idea of what to do. You just got to read the documentation to see how the syntax would be and what kind of library it would use. Programming concept is programming concept to me. I think if you understand that, you can write it in many different languages. Okay. All right. Any question? Yes, the lowest level that you need to understand, and it's going to force you to understand architecture, organizational, the components within processor, what's happening when your program is like this. So a few more minutes. I just wanted to come back to this, and I saw this on the PowerPoint slides that I uploaded. Let me go back to your CIS-11 folder. And I had uploaded the Pat Patel chapter 1 and chapter 2. You can look this over. So basically, you know, in this part, it talks about, you know, a little bit history in computing and computing devices. But the area that you wanted to think about is how are you solving problem from using assembly? Because so far you've learned a lot of different languages, right? C++, Java, higher level. But we can do the same thing in assembly, because when you're looking at a problem in software design or you go into software engineering, you're really looking at how you would implement the algorithm in your program to be able to execute to solve that problem. And so far, you've been doing that here in the other classes like 17A, 18A, 32A. But now we're going to do that here, okay? We are going to, because the compiler handled this part for us in C++ and Java. Well, now we're going to work on that here to really convert the language to the machine level. And that's why we spend so much time with number system this week. And then if you get a little bit deeper, then for the electrical and the engineering part and on the electrical side, they're doing that here, okay? So there's some microarchitecture within, right? And so we are gonna work with the instruction sets here using a specific architecture. And remember, the assembly language that you're learning is going to be tied to a certain type of architecture. And we're using RISC, ISA, okay? And you saw the category in that when I mentioned that there are a lot of ARM chips that's produced under that category. But when you're looking at Intel right? Like, for x86, this was predominantly used by Microsoft and, Linux systems. So it would use other assembly language like Microsoft ASM or NASM. Okay, which NASM is often used for browser, what you would see with like Linux-based browser like Firefox, stuff like that. Okay. Question. Okay, take a look at the presentation and kind of dive a little bit deeper in the definition and explanation of what it is. Read the book. Okay, it's important that you read the book because this is high level now and concept, and so understanding, the architecture is essential. Okay, all right, I'm gonna finish now. Thank you so much for your patience today and working with me, and I will see you next week. Put your name in the chat. Awesome job solving the problem for the lab and the assignments. Type your name in the chat, please. And see you all same channel, same time next week. Bye, everybody.
Have a great night.
Yeah, good night.
All right, good night.
Bye.
Good night.
Good night. Bye. When is the recording going to be available? Probably a couple hours from now. It does take me a little bit to get it from Zoom, and I have to convert it to YouTube. So that YouTube normally take about an hour on its own. So by maybe 9 or 10 o'clock tonight. Yeah, no problem. Just try to catch up. If you miss class, watch the other video and work on your assignments. Okay? It's okay. Yeah, I understand, Ken. So video will be available by 9 or 10. Take care, everybody. If you have no question, have a good night. You're welcome. Good night. Bye.